All right, let's look at mass spectrometry. Mass spectrometry is really a more sophisticated version of Thomson's experiment. So as you will see, if we break it into smaller pieces, nothing really new, just applications of physics that we've learned in the past. So this is a real cartoon look at a mass spectrometer. And there's a lot actually in real life. There's many varieties, but we're going to look at a magnetic field mass spectrometer because it just ties in so well with all the things we've learned about electric fields, magnetic fields, charged particles, and their behavior in those fields. So we're going to break this thing that is kind of got three, at least maybe four or more sections to it. We'll break it into smaller pieces and look at the physics of each of those sections before we put it all back together again as one big experiment. So at its core, mass spectrometry is really this technique through which we take molecules. So we're not limited to electrons now, like Thomson's experiment might have been. We can use pretty much any molecule. We have to ionize it. So there's an ionizer. Once it's ionized, then we can play around with accelerating the charges. You can see that taking place in this section here. So we have an acceleration section. And then we can do all kinds of tricks with putting these charged particles through electric or magnetic fields. And that's really where the physics lies. So the way I see it, there's really three key parts of a mass spectrometer. The first one we're going to look at is called the acceleration chamber. And the acceleration chamber is this section up here. I've just enlarged it to kind of accent what's going on in the acceleration chamber. So first of all, it's key to this experiment that we vaporize our sample. So whatever we use has to be in its gaseous form, in some sort of a gas form. So if it's a liquid, we vaporize it, heat it up, do what we have to do to get it into a vapor form. Then we're not going to talk too much about this chamber, but within here we have ionization going on. It's really important, as you will see, that we make this a charged particle. And for the purpose of this discussion, we're charging these particles positively. So the ionization chamber really is a chamber in which a process happens that we knock, in this case, electrons off of the molecule or off of the atom or whatever we're studying in order to make it positively charged. Not necessary that it's positive. There's mass spectrometers that work with negative ions. It really doesn't matter, but we need a charged particle because here's the physics magic right in here, part one, and that is we are going to take this charged particle that is drifting in this section and we're going to apply a potential difference. So in this region here, the key thing is there is a potential difference, aka voltage. And we know what voltages do to charged particles. Voltages change the energy of a charged particle. So within this section, it's not really demonstrated pretty here, but I will accent the fact that we could create a region here where there's a gap in a plate, and we make this plate positive. I'll get a red pen, we'll give ourselves another plate over here, and in the simplest case, we could say, okay, over here, we have like a negative plate. And clearly this positive charge here will come in with very little velocity, and by the time it comes here, it will have an increased velocity. And that's because we're changing the kinetic energy specifically. So what I want you to kind of pay attention to as I go through the theory here, without any numbers or examples, is just understand what's going on in each chamber. And so in this chamber, if we rearrange the formula, we're really talking about changing the energy of this charged particle by applying a voltage, and the amount of energy it gains depends on the voltage and the charge. And in the simplest case, we start with maybe zero velocity here, and we end up with some sort of a maximum velocity as it leaves this chamber. So the energy that we're changing is clearly kinetic, and so we could then break this apart a little bit and say EK final minus EK initial is equal to the voltage times the charge on the particle. So this is a generic way that we can look at any charged particle entering this electric field. Remember, this is an electric field here created by this potential difference between two charged plates, changes the energy. And again, If we want to know the speed, we can certainly take a look at 1/2 mv final squared. We can put that into the equation. And again, it's not always the case. We've got to be careful, but quite often the initial kinetic energy is essentially zero. And that allows us to kind of develop this equation that'll allow us to find the most relevant information, although it's not always what we are solving for, would be what's the final velocity as this thing leaves the acceleration chamber. So part one, the acceleration chamber, in which the change in energy equates to the voltage times the charge. All right, moving on to the next phase of business here, the velocity selector. And we'll highlight the velocity selector right here. It's this section, this small section right in here, in which we select the velocity. So if you imagine the messiness of real world, if you vaporize a sample and put it in here, the sample may not be a pure substance, and by and large it isn't. Usually chemists are trying to study very complex mixtures of different samples, and so they vaporize the whole sample, and then you get a whole bunch of different charged particles in here, all with different kinds of characteristics. So think, if you want to think about an example we can all relate to, imagine we put air in here. Now we know air is a combination of mostly nitrogen, it's got some oxygen in there, got carbon dioxide, carbon monoxide, all kinds of things. And depending on where you sample it, it may have a bunch of impurities. If that air sample goes through here, you can imagine there's many different particles that come through here that get accelerated and enter this. This section is going to select the velocity of those things. Let me show you what happens here. If you understand what's going on here, we have kind of a situation we've seen before where we have a electric field created because of two charged plates. So you can see the top plate is negative, that's this one up here. The bottom plate is positive. So we have this electric field in here, and in this case, there will be a force acting on this particle that tries to move it because of the electric field tries to move it in the upward direction. At the same time, there's a magnetic field acting on this positively charged particle, and the magnetic field will be down. So what we do in the mass spectrometer is we inject and we accelerate these multitude of charged particles, and when they enter this region, the reality is some of these things have more electric force on them, some have more magnetic force, and those things will bend. But what we're curious about is the particles that will head straight on through here unaffected. And we know the ones that go through here with this constant velocity straight line motion do so because in this chamber, they have an electric force on them that is equal and opposite the magnetic force. So again, some particles, and you can look at the math in a second and understand why, but some particles bend up, some bend down, and some go straight on through. These are the Goldilocks ones. These are the ones that, this is the sweet spot right here. They have the right velocity. Because check it out, what happens with the mass in this velocity selection region. Remember that the force acting on a charged particle in an electric field is going to be equal to Q times E. So that's charge times the electric field. That should equal the magnetic force, which is QVB, where this is the magnetic field strength. We can cancel out Q's, and we can see that the velocity of any charged particle that goes through without being deflected is equal to the electric field strength divided by the magnetic field strength. And so, magnetic field strength. And so the speed, I should be calling it speed, it's not really got a direction to it, but the speed of the particles that go in a straight line, the things that go in a straight line do so because the electric field and magnetic fields, when you take the electric field divided by the magnetic field, it equals the speed. And so again, only some ions come through here, and when they go in a straight line, we know they all have the same speed. Now they may be a bunch of different particles for sure, but the only way they go through here and make it through this opening that we have right at the end here, the only ones that make it through the opening, we can guarantee have a velocity equal to the electric field divided by the magnetic field. Anything that bends up, it's because the electric force is greater than the magnetic force. In other words, those things are moving too slow. If your velocity is too slow, your magnetic force is low, and you will bend up because the electric force is too great. And on the flip side, any particle that deflects downwards because the magnetic force is greater, they're going too fast. So pretty neat little way, just like Thomson's experiment, to determine the speed of a whole bunch of different things. That's the velocity selection region. And the math looks a little something like this, where the electric and magnetic fields are balanced, or sorry, forces are balanced, and therefore we can get the velocity. Finally, the next section we're going to deal with is the ion selection chamber. So this is the chamber that we see highlighted right here. It looks really large, but really the focus that we have is on this section right here, where if you can see, no longer has an electric field, simply a magnetic field in this region. And we can see that that magnetic field begins to cause this thing to travel in some sort of circular path with a known radius. And if it does that known path with that known radius, you'll notice that it winds up hitting this detector. So this is the path of the particle, travels from here to here, hits the detector. Again, if you'll remember, we put an impure sample in here. We accelerated all the particles that were positively charged. They headed this way. Now, the only particles that got through our velocity selector, we know have a similar velocity, but now some of them, because it's an impure sample, some might be heavy, some might be light. And because of that, only certain ones will make this exact path and end up hitting our detector down here. And those are the ones we're interested in. So again, we, at this point, know their velocity because they made it through the velocity selector. Now the ion selection chamber is going to do just like it sounds. It's going to select the ions because we have a situation, if we look at the math of it, where the magnetic force is causing circular motion. So the magnetic force is the centripetal force. In other words, the QVB is equal to the mv squared over r. We'll cancel one of the speeds on this side with speed on this side. And now, just like Thomson's experiment, we can see that you have to have the right charge to mass ratio in order to get through this magnetic field. All right, so we know your speed because we got that from the velocity selector. We know the magnetic field in here because, well, heck, we're setting it up. We're the experimenters. And the radius we know because the radius is the radius required to get to the selector. So again, now we only know the charge to mass ratio, but that's very telling. That's actually very informative to chemists especially, and physicists, I suppose, but chemists mostly use this thing here. So again, charge to mass ratio, in the end, the mathematics of this section we've seen before, the charge to mass ratio is equal to Q over M is V over, I got this right, V over BR. So I hope you're kind of seeing for yourself that each of these chambers is really kind of a different section of physics that we've done in the past. And it's really blows apart Thomson's experiment. Instead of having one place where we put a magnetic and electric field and then turn off the magnetic field, we actually have different sections for the different jobs. So in the big picture, we have this, we ionize the particles, we accelerate the particles, we put them through something that if the force, because of magnetism and the electrostatic force are equal, then this thing travels in a straight line with a known velocity. So coming out of here, we know the speed of these things because they made it through here. And then they travel in the path of a circle. And the only way they can possibly hit this detector is if in this region they have the correct charge to mass ratio to produce that radius. Now, couple of things we should understand. Number one thing, the acceleration chamber is the thing that creates the final velocity. So the acceleration chamber really, once it does its thing, it determines, oh man, I can't talk right at the same time. The acceleration chamber determines the speed. So once this speed is established at this point right here, however fast this is coming out of here, that speed is maintained throughout. So if we know the speed here, we know the speed here, and we know the speed at the end. There's no forces that speed it up or slow it down. The second thing that we should keep in mind is that the magnetic field in the velocity selector, V selector, doesn't necessarily equal the magnetic field in the ion selection chamber, ISC, if I can call it that. In other words, the magnetic field in this region right here could be, doesn't have to be, but you will see questions where it's the same in both of them, but you can also see questions in which the two magnetic fields are independent of each other, because it's really two different parts of this experiment. So this magnetic field and this magnetic field, these two fields, not necessarily the same, but definitely could be the same. So read questions carefully to understand that. So this is kind of the theory behind mass spectrometry and mass spectrometers, at least this style of mass spectrometer. You may see down the road a slightly different style, but the essence is still the same. We really are just manipulating charged particles using electric and magnetic fields in different scenarios in order to determine an unknown quantity about that particle or those particles. Applications of this, huge applications in pharmaceuticals. If you're trying to identify the active ingredient in certain medicines or anything like that, mass spectrometers are used quite a bit in the field of chemistry for identifying unknown samples. For example, the military might use mass spectrometers to identify a sample from a chemical plant that they think might be creating chemical warfare agents. They can use a mass spectrometer to basically, in the end, you get kind of this chemical fingerprint on this chart recorder. You get this kind of chemical fingerprint of whatever happens to be in that sample. So even if it's mixed up and muddled up, we can figure it out. And finally, another application, mass spectrometer is usually one of the main instruments that they use when they launch a rover onto the moon or onto Mars or any other planets we might happen to send rovers onto. Those things always carry a mass spectrometer, and that way, as they collect samples, they can analyze the sample and send the information back, and we can get that chemical fingerprint of anything that happens to be in the soil, in the atmosphere. And not only do we know what's in there, but we can also get the proportions using a mass spectrometer. So we're going to leave it at the theory for this video. It's kind of heavy, and so you might want to go back and take a look at a few things. I'll make a separate video showing a couple of example questions. Again, as you can imagine, they can be pretty involved as you go through maybe one section. That's not too bad. You might have a couple of sections in a question, and you may have a question that involves all three sections of a mass spectrometer. So we just have to take our time with the problem solving a little more because of that.